Current electricity. In this chapter we are now going through alternating currents, AC currents. What is an alternating current? How it is mathematically represented? How its effect is studied? We study a CR circuit with AC applied across it. And alternating currents. A current which flows in one direction for the first half of time and in the opposite direction in the next half of time is called as alternating current. The household current, that is the current which we use in our home, is an alternating current. Its frequency is 50 Hz. It flows for 0.01 seconds in one direction and 0.01 seconds for the next 0.01 seconds in the opposite direction. So its period is 0.02 seconds. Suppose it flows in the clockwise direction for 0.01 seconds. In the next 0.01 seconds it flows in the anti-clockwise direction. Moreover, it is a harmonic current. So a periodic harmonic current can be represented by the relation I is equal to I0 sin omega t, where I is instantaneous current, the current at the time t, and I0 is the peak value or the maximum value of current. The peak value of current is I0 and the instantaneous current is I. I is equal to I0 sin omega t. This is the relation that is used to represent the alternating current, sinusoidal alternating current. Omega is called angular frequency and it is given by the relation 2 pi f, where f is the frequency. F is measured in Hz, omega is measured in radians. We know that the frequency f is equal to 1 by t, where t is the period. T is the time interval in which the current passes in both the directions. Here the period t is equal to 0.2 seconds and the frequency f is equal to 50 Hz in household current. Graphical representation of AC current and AC voltage. Let us represent the current by a graph and try to understand the nature of this current. We know that I is equal to I0 sin omega t. Let us plot omega t on x-axis and I on y-axis. Then we will get a sine curve. From the curve we notice that the current is 0. The current is 0 when phase omega t is equal to 0. And the current is maximum in the positive direction in one direction when omega t, the phase is equal to pi by 2. And it is once again 0 when omega t is pi. And it is negative in the opposite direction. Or it is negative maximum or is maximum in the opposite direction when omega t is 3 pi by 2. And once again it is 0 when omega t is 2 pi. The period from 0 to A is known as positive half cycle, and from A to B, that is known as negative half cycle. From O to A it is known as positive half cycle. That means it rises to a positive maximum value and then comes to 0. The negative half cycle means from starting from 0 it goes to the maximum value in the opposite direction and comes back to 0. Like this we understand the positive half cycle and negative half cycle. It is positive in the positive direction, it is maximum in the positive direction at the phase pi by 2, and it is maximum in the negative direction when the phase is 3 pi by 2. We can explain these maximum values in terms of period also. The current is 0 initially, that is when the period is 0. It attains its maximum value in the positive direction after t by 4, 1/4 of the periodic time. It becomes 0 after half the period, that is at t by 2, and it becomes maximum in the opposite direction after a time 3t by 2. and it becomes once again 0 after the time t. Like this we can explain the current. A similar graph can be drawn to represent the EMF, AC EMF. The relation for alternating EMF is given by E is equal to E0 sin omega t. E0 is maximum value or peak value, and E is known as instantaneous EMF. So we will get a similar curve for EMF also. Now I will pass on to different values of currents, average value, RMS value, etc. The instantaneous value of current is given by the relation I is equal to I0 sin omega t. Taking this relation, we can define average current and RMS current, and then we can calculate these values. We use mathematical relations for deriving these relations. Here I am omitting those mathematical relations. We will learn of them in higher classes. For the present, I will give the results of these calculations. The peak value is the maximum value of current, that is represented here by I0. This is the value that is obtained during positive half cycle as well as during negative half cycle. The mean value or the average value is defined as the average over a period or over half period. The average value over the period is over the cycle is 0, but the average value during half cycle is given by the relation as average current. So whenever we talk about average current, it is the average in half cycle. Its value is I average is given by 2 by pi times maximum value of current. So 2 by pi into I0. This is average current. This average current is about 0.637 times the maximum current, peak current. The average current is about 63.7% of the peak current. We can define RMS current. Actually, it is the effective value of current, or it is called as virtual value of current. The RMS value of current is given by IRMS is equal to I0 by root 2. I0 by root 2. Its value is about 0.707 into I0. So it is 70.7 times the peak value of current. This current is similar to the DC current. The heat produced in certain interval of time by a DC current is same as the heat produced by this RMS current. So we call this as virtual current. We get a similar relation for the RMS value of the EMF. It is also equal to E0 by root 2. That is 0.707 times the peak value of EMF, E0. Now, application of AC current to a CR circuit. Consider the CR circuit in which a resistance is connected in series with a capacitor and an AC source is applied. Let the EMF of the AC source be given by E is equal to E0 sin omega t. Because of this EMF, a current flows in the resistor. The current that flows in the circuit, it is given by I is equal to I0 sin omega t minus phi. This relation can be calculated by using mathematics. Here phi is known as the phase difference. So the current lags behind the EMF by the phase phi. I0 is the peak value of current, and this peak value of current is defined by the relation I0 is equal to E0 divided by square root of R square plus 1 by omega square C square. I0 is equal to E0 divided by square root of R square plus 1 by omega square C square. Phi is the phase difference between EMF and current. This phase difference is given by the relation phi is equal to tan inverse 1 by omega C divided by R. phi is equal to tan inverse 1 by omega c by r. We can derive these relations by using integration methods, as we did in the case of DC. But they are left for higher education, and for the present we are supposed to learn only these relations. Let us discuss about an LC circuit. An inductor and a capacitor connected in series, and an alternating EMF source is applied across this series combination. Let us suppose the EMF is given by the relation E is equal to E0 sin omega t. This is the EMF applied across the series combination. Then at a time t, if the charge on the capacitor is Q and the current in the circuit is I, then the current is given by the relation I is equal to I0 sin omega t minus phi. The instantaneous current is given by the relation I is equal to I0 sin omega t minus phi. The peak value of current I0 is given by the relation E0 by omega L minus 1 by omega C. I0 is equal to E0 divided by omega L minus 1 by omega C. In an LC circuit, the current is exactly pi by 2 out of phase with the applied EMF. The phase difference between EMF and current is pi by 2, and current lags behind the EMF by pi by 2. We can prove that omega is equal to 1 by square root of LC, where L is coefficient of inductance and C is capacitance. Then the frequency of the LC circuit, the frequency of oscillation of this LC circuit is given by F is equal to 1 by 2 pi into 1 by square root of LC. 1 by 2 pi into root LC. This is the frequency. This is an oscillatory circuit. An AC EMFs applied across the series combination of LCR, inductance, resistance and capacitance. These three are connected in series and an alternating source is applied. L is the inductance of the inductor, C is capacitance of the capacitor, R is the resistance of the resistor. The alternating EMF is given by E is equal to E0 sin omega t. The alternating EMF is given by the relation E is equal to E0 sin omega t. After a time t, at the instant t, let I be the current in the circuit, Q be the charge on the condenser. Then the current I is given by the relation I is equal to I0 sin omega t minus phi. I is equal to I0 sin omega t minus phi, where I0 is the maximum current or peak current. It is given by the relation E0 divided by square root of R square plus omega L minus 1 by omega C whole square. R square plus omega L minus 1 by omega C whole square. And the phase phi is given by the relation tan inverse omega L minus 1 by omega C whole divided by R. Phi is given by the relation tan inverse omega L minus 1 by omega C whole divided by R. Omega L is termed as inductive reactance and 1 by omega C is called as capacitive reactance. Omega L is inductive reactance and 1 by omega C is capacitive reactance. And the above relations can be calculated by using mathematics. Here we are not interested in the mathematics, we are interested only the final results, the values. Summary of this